Okay, so kind of last lecture we started talking about notions of optimizing hardware basically for performance, power efficiency. We discussed these sensitivities of different pieces, etc., to energy, to delay, things like that. Today, we're going to continue talking about these power saving techniques and look at things that are happening kind of more dynamically in the system, right? Because you could do energy, power, performance optimization many different ways, and we'll keep flashing this table. But one of these ways is dynamic control of the system. And so we're going to talk about some of these techniques, specifically dynamic voltage frequency scaling and clock gating in this lecture. Quick update, this was on Piazza as well. Assignment 3 was posted and it's due, I believe, on Wednesday, the 13th. So keep that in mind. And so with that, we're gonna look first at dynamic voltage frequency scaling as a technique. This is kind of the chart that I mentioned, kind of nicely summarizes what are all the, well, maybe not all the tricks in the playbook, but most of the tricks in the playbook that you can play to be able to optimize the kind of power energy in a design, and then at what time can you do it? So today we're going to focus on runtime techniques where you're basically managing the active energy. So dynamic voltage scaling, dynamic frequency scaling, and in the first part of the second part, we're going to look at clock gating, which is kind of the inactive time, or figuring out how to not toggle the parts of the system that are not producing interesting results or are not meant to be active at all. And then, of course, next lecture, we're also going to talk about some of these things like multiple thresholds. How do you create a design where you can not only optimize the leakage, but actually optimize the balance between dynamic power and leakage in the system? Because adjusting the threshold doesn't just adjust the leakage, it also allows you to have more headroom so that you can more efficiently use some of these dynamic techniques or even sizing techniques to be able to optimize. So, but for all that, you need to kind of have some understanding of what applications you're running or what's the blend of activity versus inactivity. And it sounds all great on paper, but in reality, if you're running a variety of workloads, you really need something that's monitoring and learning about what the processor is doing. And also you need something that interacts with software very heavily. So as we'll see later, we're going to go through some of the, let's call it, control loop and circuits basics so that you can understand what are the issues at the hardware level. But we'll also touch on some of the more modern ways of doing all this, where now you really don't have just hardwired control loops. You really have little power management cores that take a lot of things into account: threads, interaction with the OS, all sorts of additional variability that you get in the system, and then try to kind of schedule something. But as any control problem, there's an overhead in figuring out what to do. And if it takes you too long, then that control action is not very useful. In fact, it can be harmful to the system in a sense of not really optimizing the energy, but burning more. So it's a very kind of interesting and very complex control problem. But the reality today is that it is one of the biggest knobs people have to play this power performance trade-off. So it's getting much more sophisticated, but we'll look first at what the origins of all this are. And a lot of these things basically originated here. And so it's kind of a nice thing. You can kind of go back roughly 30 years and see how the whole story developed. So, early 90s, people were thinking about, in a dynamic energy you have CVDD square, right? That's your term. And so, yeah, C is kind of nice to optimize, but if you can move VDD, that's a square win, right? And so there were like propositions for things like this, where, you know, it looks globally synchronous for certain task, but say you have a self-timed processor here that, you know, does a certain task at a certain voltage on its own time. If you really, all you care about is some average, satisfying some average throughput, right? You can put the FIFOs at the beginning and end, and essentially have the control look at the FIFO occupancy, right? And say, oh, is FIFO getting fuller? Meaning this clock is feeding it. This is an external kind of clock feeding this stage. If it's running faster, right? The FIFO is getting fuller. The control jacks up the supply. The processor starts working faster, drains the FIFO, right? And then you can kind of get the supply back down, right? Nice scheme. Problem is, you're adding all this FIFO read-write energy, right? So your savings here better be way bigger than what you're essentially losing here, and likely you won't be able to scale the supply of that FIFO as much because it's kind of SRAM, let's say, based. And so, you know, you have some overheads and trade-offs there, but it's a concept of how you would look at it. So then people were also looking at how can I do this, but avoid this type of synchronization, but lower the power supply for the whole system, right? So that even the inputs, so everything kind of just slows down, right? And so we'll see what are the trade-offs with that. We're gonna go back to kind of around 2000s, and a bunch of slides here are from Tom Bird's work. He's now an AMD, I think, senior fellow, so a very established guy, but like he did his PhD in BWRC, so one of the first DVFS systems that were built. And so kind of a lot of insight from, as you see, early 2000s, although they started working on it like 90, 95, 96. And so back there, I mean, there's some of these devices you don't even recognize probably, but you know, the reality was there were like big notebooks, you know, big things that were not very draining battery really fast. So people wanted to build portable things, not even like iPhone, but like little PDAs with crummy screens and things like that. And these things didn't need to operate with very high throughput and simpler tasks. And so the idea was to try to figure out how to satisfy their performance levels, but at much lower energy because the battery was smaller, right? And so they looked at ways, if my CMOS normally has a certain voltage supply in the process, can I use something else than that to be able to satisfy lower performance? Because the process was built basically to work with these types of things, right? And so if you look at, for example, the tasks that these things wanted to do is, for example, movie compression or like a little play video, right? That would be like great. And then you look at for example, the MPEG. This is inverse discrete cosine transform, like per frame, right? If you're doing certain processing in the algorithm, and you see that, you know, number of these operations per frame varies, you know, and there are basically frames with reasonable number of these transforms, and there are frames with very low number of transforms. So if you could somehow on average monitor that, this gives you, if there's a certain constant frame rate, right, this gives you some average throughput that you need to satisfy, and maybe depending on your window, you need to kind of increase a little bit or decrease, but gives you kind of a way to optimize, because you don't want to size your system for 2000 IDCs per frame, and then yet you have, 50% of the time you have 500 or 100, right? So you've kind of drained your battery that much faster. So normally what you would have is that, versus time, the desired throughput actually varies as the processor is doing certain tasks. You want, of course, a certain reaction time so that you're as a user not bored waiting for the wheel of death or things like that. Or the application which needs something done faster, maybe than the human scale, still gets it done in that time. And for that, you need to tailor a certain resource throughput. But other application may be okay with a little bit more time and things done at much, much lower throughput, right? So the question is, how do I optimally tune this throughput parameter here so that I can satisfy whatever the runtime the application needs, right? I don't want to do it faster than it needs it, because that implicitly means I'm running at higher voltage, I'm burning more power, right? And so satisfying that kind of, if you don't have that flexibility, you would actually have to sit here at maximum processor speed and then just run everything as fast as possible. People who are dictating, or applications that are dictating that throughput, will be, nominally satisfied. These guys will be ecstatic, right? Because they will finish essentially much earlier than anticipated. But that's not really kind of an energy efficient way of doing compute, because you're not taking into account that they could have operated at a much lower throughput level, right? Now, if you just go and do the naive thing and say, well, I have a fixed VDD, so all I'm going to do is scale the clock frequency, right? Then maybe this guy is okay with running a little bit slower. This guy's going to run still faster a little bit than its own normal, etc., right? Maybe this guy's just right in terms of the execution time. But note that the energy per operation doesn't change, because you've just traded power for time, right? And so if your objective is battery efficiency, I want to run certain things for a certain number of hours, like it's on all the portable stuff, and now even the laptops, you actually don't win, right? You're just changing one thing for another. Now, there are some things here where, of course, this is still a useful technique if other things are under consideration. For example, you are heating up your chip too much, right? So, and you want to quickly back off on power, right? This is still reasonable. You keep the supply, you basically scale the clock down. That just gives you a little bit more time, drops the power, and then you can correspondingly drop the voltage if you need to. But like, it is a measure that you can still use. It's not going to save you energy in the long run. Now, the thing that's a big hammer is if you can, of course, while scaling throughput, right, if you can scale the energy. So it's very rare to see, in this case, you're going from, let's say, these are old voltages, 3.3 volts, down to 1.1 volt. But nowadays you go from 1.2 to like 0.3, 0.5 volts, depending on the type of circuitry. This is a 10x reduction. It's very hard in the microarchitecture space to find something that gives you 10x, right? Unless you're, for example, tuning. What people do nowadays, you're doing like a tensor core versus a scalar or vector core, so you're avoiding a lot of data communication, a lot of other overheads that are just not a good architectural fit. It's very difficult to find these levels of gain, and so that's kind of represents like one of the most powerful techniques that people have today to manage the energy efficiency. And so how do we do this in a way that kind of rides this curve? Because obviously, you know, if I go around this curve, on one end, I'm not going to satisfy what the circuit can do. I'm expecting, let's say, here, you know, if I'm scaling the supply, I may be requiring my circuit to be at certain voltage, produce a certain delay, but my throughput is actually more, target is more aggressive. So then I'm not meeting it. So I need to kind of ride this curve as tightly as possible. Because on one end, I'm wasting energy because my VDD is not low enough. On the other end, I may be trying too aggressively, and actually I have timing violations, so my design doesn't work. Right. So around this curve, there is like some kind of, you know, let's say buffer, right? Ideally, I want to write it exactly on the curve, but normally I'd have to be a little bit above because of all the uncertainties we have in the system. So we're going to look, you know, to see what are all these uncertainties, we have to look deep in the hardware and see what the discrepancies are. Why can't we write exactly the curve? If we had perfect knowledge, we can do it, but we normally don't have, because that knowledge comes with sensory overhead, right? So what you normally have is kind of like a voltage margin that people add and say, look, you know, I'll only be able to get, let's say, up to here. And yeah, that's like, you know, let's say at that point, it's 60% of energy per operation versus the optimal of 50. So I'm paying a penalty of, let's say, 20%, but that's my buffer margin. One of the sources of discrepancy is that, you know, if you look at normalized, let's say, max F clock or delay, right, of different types of circuits, there are slight variations, right? So you see here, for example, inverter, ring oscillator, register file, SRAM. I mean, they all kind of look reasonably close to each other, but there's still, you know, some 10-ish%, 15% maybe variation, right? And so you need to include that variation as part of this buffer zone, right? Because you can't be as aggressive. You have a mix of these circuitry in a certain clock or voltage domain. It's not like one voltage per type of circuit, right, that you have. So, but with this, if we can, with a reasonable prediction of the margin, be able to get to close to that optimal voltage for a given frequency target, we should be able, for a desired delivered throughput, let's say in this case high, be able to jack up the voltage to the right place. When the task arrives with lower throughput target, we should be able to lower the voltage supply and then go back up and things like that. Of course, there is a certain overhead also in whatever needs to create these changing voltages, right? If you can have a perfect DC-DC converter, right? Very high efficiency, that will be the best with continuous kind of tuning. But some of you who are working on that, no, it's not that easy. If you have an LDO, you have these overheads because it comes from fixed supply, right? But it's kind of relatively easy to put on the chip, right? And so people have tried all sorts of various schemes even for those blocks. And the overhead of controlling and how quickly you're switching the supplies also matters. So we'll see some examples of that as well. But if you're doing it with reasonable separation, in these systems, it could be like seconds between tasks. We're not talking about nanosecond level switching or even microsecond level switching between tasks, because a lot of these supplies, of course, have decoupling cap, have big capacitance that you don't want to just drain too quickly. you want to kind of ride that curve with a little bit slower time constants. So the key thing is that the operating system really wants to set the processor speed, right? So you could do all this like in a tight hardware loop, right? But ultimately you want to leave the flexibility for the OS to recognize, oh, I have a big task coming up, I need to prioritize this, or I want to be in a lower power state, battery power saving just kicked in, and I want to kind of, it's okay to slow things down just so I can prolong the battery lifetime a little bit more, right? All these things the OS needs to intervene, right? And so you need basically a voltage scheduler that will turn the kind of desired throughput or target into what voltage you need to run on to be able to complete this, right? So this is kind of what I was saying. Let's say the MPEG example, you know, as the frame goes by and you're adjusting this kind of how many, let's say, IDCTs you're doing and things like that, you're kind of varying the, of course, you know, it's megahertz. In this case, you know, we're talking about like 0.6 micron process, 0.5, as you'll see some examples. But you do have these kind of a fraction of a second level adjustments, right? And of course, it's also like, how granular are these adjustments? That depends on the voltage regulators that you have and that you're trying to use. We'll see later, there've been examples of just dithering between two states, right? Because it's just very easy if you do switch cap ratioed converters, they're very efficient, but they can only give you a few discrete supply levels. The question is that enough, or do you really need to ride the continuous curve, right? Maybe you don't. In fact, in many other things, we've seen that piecewise approximations or things, coarser approximations give you basically 90+% of an answer. So why bother with that diminishing returns fraction? Because you're significantly increasing the complexity of your voltage scheduler or the regulator, things like that. Okay. So an example of, you know, how this converter loop would look like is basically done by Bird. And so we're just going to walk through this. So you're trying to essentially regulate the supply on the processor, right, for a frequency target that's essentially set by the OS, right? And so you have this ring oscillator, which is really a frequency sensor, right? Ring oscillator will give you a certain counting frequency for a certain supply voltage that you have. The higher the supply voltage, the higher this F clock is. So there's some monotonic curve that this will generate, right? So in terms of, if you had a counter here and you were counting the clock cycles from, let's say, comparing to a constant reference of 1 megahertz, you'd be able to see, if you jack up the supply, you'd be able to see the increased count compared to 1 megahertz, right? If you lower the supply, you'll be able to see the lower count. Right? And so this F measurement, the digital thing, can be compared to something, to a desired value that the OS sets. So the OS could say, oh no, I want to run 10 megahertz, 100 megahertz, 50 megahertz. You'll be able to count this. And then of course, if you're above or below, you can essentially low pass filter this into a trend. I want to keep increasing the supply, keep decreasing, and ultimately dither around the point where these two things are equal, right? And that drives essentially a buck converter, which will, you know, pulling more energy for the supply or draining more energy from the inductor so that your VDD can go down, right? And of course, you need to set this loop dynamics so that you have a reasonable filtering here and you have a reasonable decoupling cap that you have on the chip, right? Now, the key thing here is that this ring oscillator, it's not just enough to basically just count some frequency, right? Or the reason why you're capturing the FV relationship here, you believe that for a certain voltage, a certain frequency realization that represents the clock cycle on the processor represents the types of circuits you have on the processor. You're basically using this as a replica of what is the critical path inside the processor, saying that, oh, if I had a critical path on the processor here, and I set it to the same VDD, right? It should work at the same, it should track or produce, require this clock frequency that tracks this FV relationship here that comes out. That's very important. Otherwise, if this is, let's say, predicting a faster operation than what's inside, right? It will tell you, oh yeah, it's okay to lower the supply further. I'm still okay. I'm not meeting the frequency target. But then guess what? Inside, the actual critical path is not satisfied. Right? And so we're going to see a few more techniques of how people try to enhance this, because obviously a ring oscillator on its own is not really a good representative of everything that can happen in critical paths in logic and sequential circuits. So people try to kind of make this more sophisticated, but this is basically kind of the basic mechanism, essentially, if you will, if you wanted to do a complete kind of control loop that does basically this DVFS. Of course, we'll see that in reality, things are a lot more complex. You need to figure out where is this thing coming from. There's a lot more complex problems sitting behind deciding what this desired frequency needs to be, right? And also what actually runs on this processor. This is not just an IC, discrete IC, it's actually could be multiple cores on the same chip, different domains. How do you allocate tasks between these cores, threads, and things like that? So we're going to talk a little bit more about that as well. Here is an example of lifting up to that higher level, right? This is, for example, one of the snapshots from one of the let's say recent Apple patents, right? And what it's trying to basically show you that there is some digital power estimator circuit block that essentially what it does is it monitors all sorts of events on the chip. Something got launched into a register, the unit started executing, etc. So you're logging these, they call them, let's say, digital power estimator events, right? Each one of these events is pre-characterized with some understanding of what's the power of an add or a multiply, things like that, right? And the control circuit keeps track of that. So it's trying to establish an understanding of the overall average energy draw in some window of time. And there are some automatic power state controller events. Again, I'm deciding a certain balance between the different cores, a certain DVFS state, and it kind of munches all that together and uses things like these types of control tables. If you look at here, for example, there are, let's say, 4 cores in this system, right? So in the first 2 voltage frequency settings, these are like tabulated. How do you come up with these tabulations? Maybe it's process characterization at some number of wafers. Maybe it is from the built-in sensor calibration circuitry. You have these power-up sequences or periodic recalibrations. You can do all sorts of these tricks. But the ultimate thing is that you come up with some voltage frequency pairs that you want to exercise in your system. And then it also depends on the number of cores that you can afford to run on that system for those voltage frequency settings, right? So for example, if your voltage frequency setting is too high, right, you may not want to run all 4 cores at that, because you're going to be heating up the overall power limits of the whole package. And So you want to limit that, in certain settings, you can only run 3 cores or 2 cores or 1 core, right? And then so those are kind of these limiters that tell you for certain application, a given voltage frequency profile, I can run this many cores maximum, right? And so, these types of things are really kind of like a small processor doing things, right? Collecting information from sensors, looking at some pre-calibrated lookup tables to compute what the next events are and things like that. You can also look at kind of how really the DVS-FS gets scheduled, right? Think of it in a way of, this is now at the higher level that we're talking about, where you don't have just one ALU on the chip, but you have a number of cores. And these cores could also be different size. We'll see later that Adler Lake, for example, has, as well as some of these, let's say M1, you have big cores, like let's say 4 of them or 8 of them, and then you have small cores. And you call one performance efficient cores and other energy efficient cores. So if you have a high performing task, it actually pays off more to throw it at a really good core, which can finish in a reasonable amount of time, than run it for a very long time on this low power core and overlap kind of a lot of operations. It's not energy efficient because you're fetching the data, bringing it somewhere back, etc. Plus it annoys the user, right? And so there are these balancing that the OS needs to basically decide, right? But you have a map of all cores running full frequency, max frequency, max voltage, right? To a single smallest core running at lowest frequency, lowest voltage, right? It's kind of like a 2D map. And you need to walk that map as a scheduler as you look at the bunch of threads and applications and decide how you want to drive it. It's not an easy problem, right? It's a lot more complex problem than that simple DVFS loop that I've shown you, right? So you can use this controller that I described once you know what your voltage frequency pair is for a given subset, right? So that's basically kind of like let's call it an operator, right? I want this. There is a hardware loop that can do that for me at the lower level, but I need to walk this map to understand what do I want in the first place, right? And I better not take too long to do that because that decision may expire because a new set of threads can come in and change what I want to do. So I need to kind of balance this coming up with a desired voltage frequency setting with basically, how frequently do I come up with it and how precise that desire is, right, to optimize the power. So to be able to do that, 2 things, what we just described as like walking that map is really just looking at, can I satisfy the performance that the user wants, right? But to know that you also need to, of course, optimize the energy, which is another axis. And for that, there are 2 kind of things, right? One is you do need to monitor the short-term power draws and temperature, because despite my best desires to complete a task at a certain given time, it just may so happen that the previous set of tasks or whatever was going on was pushing me toward higher performance. And so I really heated up my processor. I need to, at this point, I'm not operating at max voltage, but it just happened to be a long enough window that just my whole package heated up. And now temperature is a third variable that we didn't talk about. Like every voltage frequency curve is parameterized by temperature, right? So that one optimal line that I have actually becomes a family of lines that's temperature dependent. So if the history of the task was pushing me toward the worst curve in terms of temperature, I can't now go back to the high performance mode. I have to kind of slow down let things cool off, and then keep going again, right? And there are different ways in which this temperature backoff happens. Sometimes it's catastrophic. It's really going to melt the chip, and you got to shut things down or drop the clock and then drop the voltage. Or they're just like early signs, and you can start basically dropping the voltage, hiding that under some application or thread that doesn't really matter that much or impacts, but you have to do it anyway. So there are all these decisions that need to be made. And so that's why it's important to look at both short-term power draw, temperature, and also monitor kind of the average energy within some history, so that you can actually do what you wanted to do in the first place, optimize the energy on average across a bunch of tasks in a period of time, right? So to do this, another question comes at the programming level is, do you do this for, it's easiest to think about a single thread or a single program. Okay, something executes some serial line of code on a certain core. I'm gonna, even at compile time, look at this, and then I'll have different hooks as I'm launching these instructions to basically trigger what these events are. Each event will be labeled with some energy need, and I'll estimate roughly based on that whole thread when it needs to complete. So I can do all this power management computation in this PMU. But in reality, that's not what's happening. You have a beast, let's say here, 8 performance cores and 8 energy efficiency cores. So 16 cores. They all want to run. In reality, only a few of them run. And then in a burst, all of them want to run because someone really wants to hit it hard. There's a lot of things happening. So the scheduler needs to really understand what's the state of each core, what the occupancy is. It also wants to group. The new thing here is these thread groups, right? You look at each thread and look at types of computations and resources that it needs in these operations. And you're trying to group the threads by similarity so that you can perform the scheduling of voltage frequency and on which core it goes on the group rather than on a per single thread. So that makes things a little bit easier because you're bundling. If you have 100 threads, maybe it's 10 groups. So the problem dimensionality becomes smaller. But you also have to handle the cases, what's the dissimilarity between the threads? They're not all identical. So there's some things you need to keep track within the group so that they can all execute. Because if they're not identical, they have a little bit of a distribution, you're not going to get the best energy saving. One of these threads that's still in the group is going to screw things up, right? But maybe the discrepancy there is small enough so that this thread group compared to this other very low performance thread group can be very easily distinguished, right? So as I said, there are many levels. Of course, it will take a whole course to go through all of them, but just to give you a feel that this is, even though this is a circuits class, there's a lot of issues here that software needs to be aware of. And in fact, the sad thing is, despite of all this technology that we have in hardware, some operating systems just don't use this very, like you look at Linux, it's not very good actually at doing certain things. Of course, you could think of Apple's version of Unix or like whatever, let's call it the version of Unix, like Apple OS is let's say a lot more sophisticated at doing these things because it's their processor. They write the OS. They really want to make this interaction very, very close. But if you're writing an open source OS that should serve a whole bunch of computer architectures and processors, it's hard to have these lower level things that will interact very nicely. People do write in all of these processors, you have like a dedicated, basically power manager core. So an integer core with some memory, you could think of a rocket ship being that. In fact, in many architectures, it is. Runs its own code. It's called, let's say, P code in Intel. So you write this firmware, let's call it, that interacts with the OS and helps manage things, but it's not easy. You need to really adapt this to a particular architecture. Okay. Going back to kind of the lowest level, how do we know where to get these voltage frequency curves in the first place? So we need to understand all these different levels at the circuit level. Circuit design constraints, how do I verify this, right? Functionally needs to do the same thing, but now not at a given voltage and frequency, but over a range, right? That has to do with circuit delay variation. Noise margins are now reduced, different than, let's say, at full VDD than as I'm working at a very low VDD. Power grid, coupling, all these things, delay sensitivity. Right? So the question is, how different is this design than designing for a fixed VDD? Right? And what additional things we need to do to make sure it works across a range? So again, we had this curve basically of different logic circuits and normalized F clock versus VDD. Well, let's say, in this range between 2VT and VDD, NMOS pass gates, for example, become a problem, right? Because you have an additional threshold voltage drop. And so you end up not shutting off the thing you're trying to control, right? In terms of functional verification, you really only need one VDD value because you're just trying to check the function of the thing. But for other things, you do need to watch out what your delay profiles are. Like, for example, here, what they've done here is, there's actually another paper that kind of really shows this from earlier on. You design essentially, let's say, an inverter chain, what with different properties affecting the delay. Right? As we all know from 251A, if you write the Elmore delay for an inverter chain, you have all of these a mix of RCs, right? You have a gate dominating, you have R wire, R1 of the inverter. So if you have a lot of gate load, right, there will be a certain type of delay characteristics. If you have a lot of wire load, because that doesn't change with voltage while the diffusion and gate capacitance change, there will be a different kind of profile, right? Your R-on will change, but C wire is not going to change. So you have three different types of capacitance: diffusion, wire, gate. They all change differently with voltage. And then you have R-on, which also changes with voltage, right? And then you have R-wire, which doesn't quite change with voltage, except if you're heating things up a lot, and then it does. So they plotted these variations, right? Essentially across VDD, right? So let's say a gate-dominated one is kind of concave, right? And then the other ones are kind of more convex. But there's going to be some blend of these things, all different types of logic circuits, right? So what you're trying to figure out is, if I'm doing timing verification on all these spots, right, where should I do it, right? Should I run it here or here, right? And at least for this study, they basically figured out that because a lot of curves are convex, and then some are concave, you can actually do the verification. Given these margins, you can basically do the verifications and min and max VDD, and that's going to be enough, because that's where your biggest kind of excursions end up being. But if let's say all the curves were concave or all convex, you could have somewhere a minimum showing up kind of anywhere in that range, and you need to catch where that is and then do the verification there. So it's still worthwhile doing these types of curves to understand for your mix of circuitry, your process, what it should be, and then determine where you need to characterize. Now, we did mention that there are more sophisticated ways of tracking than just basically looking at a single ring oscillator chain. Even within the ring oscillator chain, as we saw, adjusting the gate to wire to diffusion ratios, you can get different things, right? But you can be even more explicit. And typically, a lot of logic is built out of NAND gates, right? You can have NAND, NOR, let's say some example of adder XOR is basically or wire or pass gate. Right? And then what you have here is essentially different critical paths. You have the launching register, and then you have the edge detector circuitry. And what all this does is basically tells you, depending on what the controller selects is the critical path. Here it tells you for a given voltage setting, as you launched, and given frequency here, as you launched the data in, how far did the edge come? Right. This is basic. Edge detect is essentially, like a time to digital converter. Tells you, okay, I know roughly the delay. This is like, for example, in this case, fan out of 2, right? So you know roughly what a fan out of 2 is. And then you're essentially looking at how many of these delays you got in and reading off the overall variation, relative variation between all of these different paths. And that's kind of essentially summarized here versus voltage. So you can see that different paths, again, it's very similar to the previous results, like 5%, 10%, maybe variation, up to 16% here. If you look at the absolute, right? And then some number of, this is actually picoseconds, and then some number of RMS variations, because you can actually disperse these measurement circuits throughout multiple cores, wafer to wafer, look at all those statistics to figure out, is your technique robust across million chips or 10 million chips that you're going to produce for people, not just like on one wafer. Different types of, again, circuitry. This is, again, something that was done. You see different types of, inverters, NAND, NOR, heavily interconnect dominated one, and a similar kind of, tunable delay line with essentially a TDC, so that you can capture or digitize this information. It's very useful to have these as small digital self-contained blocks that you can just sprinkle around your system to be able to figure out what's going on in different power domains. It's a little bit of a different story on the SRAM side, because you have bit line discharge, you're activating a long capacitance word line. You have to, so it's kind of like different types of circuits driving different types of capacitances. And versus voltage, it ends up being hard to track those timings. When should your sense amp fire? When has enough voltage being developed on the word line, right, for a given overall supply voltage? Because if you think about it, if I change the supply voltage on the memory, right, on a read, the cell that's pulling down basically has a reduced drive. So it will need more time to get the bit line to a certain voltage that you can actually sense with the amplifier. Sense amp is also going to be affected because the lower its own supply voltage, the more of the input voltage it needs to compute in a given amount of time, right? So you need somehow to track all these things, or at least be able to configure, right? So people use, for example, timing replicas, right? So you have a timing replica where you can configure the number of read lines, read cells that give you a certain timing delay between, let's say, the word line going up on the main and you triggering the sense amp, right? But then they also build these types of circuits where they can, like a forward, backward. It's basically a delay multiplier. So if you have here an event that discharges too fast and you want to give yourself more time, you essentially configure this delay multiplication circuit. So you add, a factor of, let's say, 3. That way you don't have to change the number of cells that are discharging, because you want to, the more cells you have here, kind of the less noise, or the stronger the current is, so the less noise in that 1 unit timing estimate you have. But then you have to multiply up that delay because it may be too fast. Right? That's just one example of how people do it. Now, other techniques that people have used is saying, okay, well, I'm not going to have really replicas because my replica is never going to be exactly what I want, right? It's not exactly the critical path that I have. So what I'm going to do is essentially have all of these error detection circuits. So I can detect when an error is happening in my pipeline stage. And that's a signal to me that I'm too aggressive, let's say, on the voltage, stepping the voltage down or increasing the frequency. Right? And then I can basically replay. So if I did a pass, I was too aggressive, I find an error, I will basically replay the instruction or part of the instruction in the pipeline stage. And then I know what should be the right setting, right? Of course, that comes with additional overheads. First instruction replay if you're wrong, then also this additional checking logic, depending, do you want to do it per stage, etc., or per whole unit, things like that. One thing though that it's good to just keep in mind, we didn't really talk about it earlier, was even in the core DVFS loop, and this may be thing for you to think about a little bit. If I have a certain voltage frequency setting, right? And I get a command to perform at lower power, right? So green light is given to basically reduce performance. Which step should I do first? I can lower the clock, right? Or I can, in the Thunberg's thing, it doesn't tell you exactly how the clock is lowered, right? It has this fixed controller, but something inside has to lower the clock as the voltage comes down, right? So you have to know, something has to tell the PLL, and we'll learn what PLLs are, but clock source needs to lower the clock, right? Frequency. So you're at a certain operating point. You want to lower your frequency and supply. Which do you change first, voltage or frequency? You want to keep running, producing correct results. Yeah. Exactly. That's exactly right. So you first drop the frequency, you give yourself slack. And the next thing, you are basically changing the voltage to fill that slack, right? And of course, you need to make sure that your frequency step versus your voltage step is not such that when you make, let's say a reduction by 1 notch in frequency, that your voltage step kind of goes over, right? So you have to make sure that that's true. But that's and okay, on the other way, right? If you're going higher performance, right? You wanna do what? What happens if you keep the voltage, but you increase the frequency? Does that work? I mean, you want to increase the frequency eventually, but if you're at a certain voltage, can you just increase the frequency? Likely no, if you did a good design, right? Because you were kind of close on the slack. You're riding that curve reasonably well, right? So the first thing you want to do is, again, give yourself more slack toward higher performance. So you boost the voltage. The circuit operates faster for a given frequency. Then you increase the frequency to close the slack. So this ordering has to be basically built into the algorithm so that it knows what to do first. Yeah.
But couldn't you like violate the code type if you just simply scale the VDD first?
It can, but you should your whole time. This goes back to how you're characterizing your whole circuit, right? Hold time doesn't have anything to do with what the cycle is or what the frequency is, right? So if you characterized your circuit for highest VDD or let's say lowest VDD, you should be set, right? Unless there's some weird scenario, which, looking at these delay profiles that we saw shouldn't be there, that somehow somewhere in between, for some voltage in between, you get a hold time violation. Let's say a clock register mismatch versus some short wire delay or simple logic gate mismatch. Okay, so some more circuits considerations here, right? So how do you, deal with some of these things? Well, we already talked about it. These are like some of the laughable numbers, like 0.6 micron. But the key thing here is that CMOS scales reasonably well. It's established that it has this nice voltage frequency or delay voltage curve that you can ride up to a certain point. One thing you need to pay attention to is as you're increasing the supply toward a certain point, you want to look at essentially the dVDD/dt targets, because for given capacitance of the, let's say, supply, that gives you the ripple. And so you don't want to design your system for low VDD, low dVDD/dt, because at low VDD your transients are going to be slower, right? And then all of a sudden you want it to operate at higher voltage where you don't have enough decoupling cap or even the power supply network to be able to handle now these larger spikes, essentially, right? So you have to make sure that dynamic aspect is basically satisfied. We see that, what we mentioned earlier, ring oscillator reacts nicely to changes in supply voltage. This is just basically as you increase the voltage, the count kind of increases. One thing that's a little bit tricky, luckily that is not really too big of a deal right now because we don't use these things too much, but in the last, let's say first half of 2000s, the first decade, people still use dynamic circuits up till 2004-5 in certain very high performance parts of the ALUs and things like that. And so if you start doing these voltage scaling things, you need to be aware of what's happening, because your dynamic logic may be remembering a certain voltage value that came from a previous supply setting on that transition, right? And then it may drive that gate either into a fail mode because it can't drive the other gate, it's underdriven, or it could drive it into a complete fail, like a latch up, because it now overshoots the supply compared to the previous one, right? But the issue is still with tri-state buses, right? So it's kind of a tricky thing. If you have a bus, you tri-stated it, means its output voltage stayed at previous VDD, right? Whatever that VDD of that bus was. Now, if you change the VDD, that voltage is no longer going to be a true representation of your power supply. It may affect the next stage. So you need to be careful about how you handle these types of things. The promise of what we set out to do actually does hold. This is kind of the measured MIPS, instructions per second. So yeah, if you're willing to drop the instructions per second, your basically energy moves correspondingly, right? So you can actually get the operation that you want. Now, I did mention earlier that maybe you don't need, people have looked at whether you need continuous voltage, or you could basically just maybe discretize this and have the only a few voltage levels between which you're actually dithering. So this is kind of the same study. Look at MPEG-4, and as you have different types of slices of the application, what it's executing, right? You're choosing the number of essentially frequency levels or correspondingly voltage levels, right? And you look at power. Hey, at 2, I'm getting like 90% of my gains, right? And I'm 3, 4, blah blah blah. It's like few percent more, right? But the overhead in creating, and in fact, if you wanted a smooth curve, let's say you would do an LDO, just that choice kills basically all these gains that you can get here. So you might as well do like a 2-level switch cap converter and be done with it, right? But of course, this is for this application, MPEG, right? Other applications or mixes of applications may create a more complex environment where you still want to have some number of discrete states, right? And that's usually people have to pay attention to. So this is an example where they just implemented essentially that thing. You have two states, half a volt and let's say 0.6 volts, and you show kind of the dither between the two of these states, and the power supply is coming from a switch cap, right? So you can collect some gains from there. And if you look at kind of the curve, this is what I was saying. For example, versus time, this is the ideal curve. Bypass mode means like I could give you the exact voltage you want. Right? If you do the fixed DC-DC or with dithering, you're basically writing this curve, which is approximate and reasonably close. But for example, if you chose LDO, because of the overhead of the LDO itself, you're kind of writing, but you're not really kind of exploiting. You're kind of leaving a lot of energy on the table just because you chose that regulator architecture, right? And that's kind of interesting to note that some approximations with a more efficient converter can help you actually get to the goal better than if you're exactly trying to track the voltage frequency curve, but your overhead is bigger. Okay, let's see how we're doing it. Yeah, I think we can cover. So that's just a really fast intro into the world of DVFS and what are all the issues. We're going to talk a little bit about clock gating. This is kind of a very frequently done optimization now, actually also by a lot of EDA tools, so you don't have to worry about it. But it's often a good thing to check what the tool has done, because the tool doesn't often do the smartest thing, and you may need to, depending on your design, to go and explicitly tell it to the clock gating. It is, again, in our table, kind of a way to reduce the active energy, because you're preventing, let's say, a flop from being triggered by a clock in case it's not producing really any new result, right? So there's no need to update that. Flops burn kind of most of the power if you look at the overall digital system. So if you could even just prevent flops from toggling, that's a big save. Right? Like if you look at, for example, this is like some DSP circuit design, doesn't matter, that I pulled just to show you, you have this activity of the flip-flops, right? And you see that there's a lot of flip-flops basically just really not being active. What do we mean by active? On the next clock cycle, giving you a different result, right? So a lot of flops just sit there and basically just give you the same thing every cycle, even though you're clocking the whole thing. And so you really want to try to minimize that. Right, so conceptually, what I would want to do is have some enable signal that comes from some state machine. So this is just a D flip-flop that basically represents part of that state machine. that came up with an enable. It's of course clocked by some common clock that we have in the circuit. And I have a buffer on that clock as I'm distributing it. And I want to insert this gating cell, right? That will turn this clock signal into a gated clock signal. So whenever enable is 0, let's say I want to disable this clock domain, right? Then the gated clock signal will become 0 regardless of what this clock signal is. Right? But it needs to be done in a way that the properties of this gated clock signal remain clockish, right? It has, what is a clockish? Well-defined duty cycle, high-low levels, period, right? You want it to be clock, not some glitchy thing, right? That basically upsets the operation of these registers. You also want it to be low noise, right? So this circuit cannot be something very complex where it adds a lot of jitter, right? So all of these things need to be taken into account. So I give you just the two basic kind of blocks, right? Of course, if I go back here and I just add an AND gate, kind of a naive way to do it, right? We could hope it accomplishes the task, right? But let's see what's the kind of subtle problem with it. So if I take basically just the AND gate and I stick it into that gating cell, right? You get a situation on the top. You have a clock, right? That's happily coming into one of the inputs. And then because the enable, remember, was generated by the same clock from a state machine, it has, let's say, a little clock to Q delay here, right? As well as, let's say, from this edge, it's a little clock to Q delay to change. Well, because I'm now ANDing the two things, right? I'm going to create a glitch here because the gated clock is going to be an AND of these two. Right, so I get a little one here that I then immediately drop to 0. That's fine. This is fine. This is fine, but this is not fine. Right. And so these glitches, depending how wide they are, they're first of all adding overhead because my flop is flipping. If they're too narrow, they could actually get flopped to misevaluate, right? And that's even worse. So I don't want to have these glitches. So how do I deal with that? Is I can build essentially a circuit like this, where I add a latch. Now this is no longer, this is a flip-flop, so it's edge triggered, right? And if the flops in the path are positive edge triggered, like in our example, you would want to have this be negative level sensitive latch. And in that situation, you're kind of only letting this latched enable become active when the clock is low, right? There's a little, let's say, clock coming down to Q just to establish that value, but it doesn't matter because that's the low period for the gated clock anyway, and you have this whole half a period to basically settle, right? And then you essentially get the gated clock. And the latched enable doesn't change when clock is high, so that's nice. It keeps frozen, and then it only changes after the clock goes low. And because the enable changes somewhere in between, that doesn't matter. The latched enable is still stable and passes the 2 full pulses of the clock very cleanly, right? Okay. So this is called, like, let's say, an integrated gating cell. Because you really need to, this very nice behavior definitely depends on the delays on these paths, right? So you can't just you can, but with great risk, let the tool go and put a latch somewhere, put an end somewhere, and then, hope that this is now your gating cell, because you may get different wire delays. Who knows where this is, right? People build essentially one single cell that contains both an AND and a negative latch, and then that cell is just inserted into the clock tree and very well characterized, so the tool understands what are these little overheads in delay that it needs to pay attention to not create glitches in the network. Now, how do you use this? That's a different story. So I'll give you just a few examples. Here, for example, this is from Brooks. It's a pretty nice paper that talks about a few ideas. But let's say you have a processor pipeline stages here, right? And your integer functional unit is 64-bit wide. Right? But a lot of operations have essentially data values that are not spanning all 64 bits. In fact, they're in the lower 16 bits of precision. Right? So if you can detect the leading some number, in his case, it's like 48 leading zeros, right, on both operands, then I know I have a zero in basically those, for example, for this type of operation. So I don't even need to update my register or clock it, and I'll just pass the zeros as basically the upper 48 bits of the result. And so I will gate the upper 48 bits, but normally clock only the lower 16 bits of my pipeline register. Right? And so then as you're doing kind of instruction launch and you're looking at data operands, these zero detection circuits basically tell you whether you should gate the clock in the next stage when you're actually doing operations or not, right? So that's one example. Another example is, for example, looking at the activity within the cycle, right? And this adds a little bit more explicit overhead, right? Because what you're doing here is you let the logic compute the next result, and then you're just comparing it with what was there. The logic was computing something that's already in the hop. There's no need to trigger. But now you have the additional critical path overhead of all this stuff, right? And the question is, well, does that additional timing overhead justify the energy savings that I had? Because, you know, in DVFS, if I had extra slack, I could just lower the supply, right? So all these are possibilities for optimization, and really depends on the technology, on the application, which one of these knobs you want to turn. Right? But it's there. And of course, you know, I would say nowadays these types of things are kind of for very specialized types of ASICs that have predictable functions. In more general purpose compute, you wouldn't necessarily do this because you would rely on all these other knobs you have in the PMU to kind of more, let's call it, digitally control the whole system, right? Rather than some local optimization loop that misses the point of the bigger system optimization. Right? So premature, in other words, there's a saying that premature optimization is a source of all evil. You know, so anyway, and of course, you know, the potential penalty, as we said, of doing what I've just shown is that, you know, you significantly increase the number of critical paths now with a negative slack because you're adding that extra delay, right, in a bunch of places. Okay, so next lecture, we're going to do more power saving techniques, look at multiple thresholds, sleep modes, so kind of more detailed look at how does this power management unit deal with different states and how does it interact with the OS and things like that. Okay, any questions about this? Thoughts? Okay, I know it's a lot, but I think it's good for you to get exposed at least to everything that's there, so you can be aware of the issues. Okay, thanks all. Okay, we're gonna close it because we're done with the lecture. I guess, Bora, you can stop recording.
Thank you, Professor.
In front of the library, you mean?
Yeah.
Oh, interesting. How do you check if I'm addressed?
Oh, yeah, I think you're right.
I think like a